So hello everyone, good afternoon, how are you all? So we have Manoj here, Apurv, Siddharth and all the candidates who are present here. The topic that we are going to discuss today is radioactivity. And this radioactivity is important for examination because previously there are a lot of questions which are asked in the CGL examination. So not only CGL but also in all the other SSC like SSC exams like whether it is CHSL, whether it is CPO or if I talk about the railways examination also. So yes, this topic is important. So the questions can be like the alpha ray is equivalent to what, or beta emission is equivalent to what. Apart from that, which of the following has the highest penetrating power? So these type of questions are asked. So yes, I will create one of the confusion, the small confusion, but obviously I will be trying to solve it also. So my first and basic question is, guys, who discovered radioactivity? Now you must be wondering, sir, you have not explained what is radioactivity. Why you are asking this? I'm asking this because I want to make this very clear that Curie did not discover radioactivity. Okay, so it's not discovered by Curie. So neither it was Marie Curie, Pavan, nor it was Pierre Curie. Then who discovered it? So let's start with the chapter, then I'll explain. So first of all, let's start with this radioactivity part. So see what happens. As we are aware of, in the modern periodic table, there are total 118 elements. How many elements are there? Total 118 elements are there. Now, these elements, out of these 118 elements, there are few elements which, because they are unstable, they emit alpha, beta and gamma rays. Why? Because when they disintegrate, they tend to have the more stable nucleus. So for the stability, they keep on disintegrating itself. This process is known as radioactivity, and the elements which undergo this process are known as radioactive elements. So there was a question which I asked in very starting. So who discovered radioactivity? It was not discovered by Marie Curie nor Pierre Curie. So it was discovered by Henry Becquerel. So I have started my chapter now. Now I'll be able to link each and everything. So yes, first of all, let's start with the radioactivity. What is it? So the nucleus of some elements are unstable. So such nuclei undergo nuclear decay and they get converted into more stable nuclei, and during this reaction, these nuclei emit some harmful radiations and elementary particles. So the phenomena of nuclear decay of certain elements with the emission of radiations like alpha, beta and gamma rays, that is what radioactivity is, and the elements which undergo this phenomena is known as radioactive elements. I won't ask you about the examples because you all are aware of. Example can be like uranium. Fine. Okay. So yeah, sure, no worries. So here I'm repeating it again. So guys, the topic that we are going to discuss today is radioactivity. So the nucleus or the nuclei of some of the elements is unstable, and because this nucleus in us is unstable, so nuclei undergoes nuclear decay and gets converted into more stable nuclei. And during this process, since it is disintegrating, so there are some harmful radiations like alpha, beta and gamma rays are actually emitted from here. This process is known as radioactivity, and the elements which undergo this phenomena is known as radioactive element, and the example is uranium. Okay, so as we have discussed, so it's not about each and every element. There are only few elements in the periodic table which undergo this radioactivity. Now do you know which elements are there? Siddharth, let me complete my statement, then I'll come back to you. So Siddharth, the point is, as discussed, there are total 118 elements. And from the next class, we'll be starting with the chemistry. So I'll teach this tomorrow as well. Just want to know, the modern periodic table, which was discovered by Henry Moseley, it is based upon what? So the modern periodic table is actually based on atomic number, right? So yes, all the elements are arranged in the sequence order of its atomic number. Hydrogen has atomic number 1, then helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on. So when we'll talk about the atomic number 82, Siddharth. So the elements which have atomic number greater than 82, that is 83 plus, they all are radioactive elements. Now tell me, which group is considered as the transition elements, which are transition metals. So can you tell me about the block, Siddharth? So that is P block, right? So here I'll tell you, if I'll talk about the F block in that actinide series, the one that will come under this category, right? And apart from that, there are two elements which are lesser than 82, like promethium and technetium. So I'll just show you by a periodic table for better clarity. Yep. So here, this is that periodic table. Now just have a look. As you have told us, from this to this section, this is under D block, right? This is S block, this is P block, and this is F block. So the elements which are radioactive elements are present here. So the best part will be the elements which are greater than 82. That starts from bismuth. So 82 is the atomic number of lead. So after lead, all the elements till 118 are considered as radioactive elements. So yes, there are a few of them who are in from the transition metals category, and all the elements which are in the actinide series, but two elements, that is technetium with atomic number 43 and promethium with atomic number 61, are also radioactive elements. So I guess, Siddharth, now your point is clear. So in lanthanide series, only promethium will be there, Mr. Siddharth. Fine. So let's go. So elements like uranium, radium, they undergo radioactivity and they emit radiations on their own without any human intervention. Since there is no human requirement, so it is said to be natural radioactivity. So the question that one of the students was asking, so that line is here, the elements whose atomic number is more than 82, they undergo spontaneous radioactivity. So uranium, radium, all these are under the same category. There are only two elements which are radioactive but their atomic number is less than 82. So it's technetium with 43 atomic number and promethium with the atomic number 61. So as of now, 29 radioactive substances are discovered, right? But yes, most of them are rare earth metals and transition metals as discussed. So I guess this part is clear. Any questions, any doubts, any queries? Tell me. So that's clear, right? Okay. Now guys, we have understood this by the periodic table. This is modern periodic table. This will be the part of the chemistry from the next lecture onwards. And this periodic table was actually given by Henry Moseley. Who gave it? This periodic table was given by Henry Moseley, and here elements are arranged in the increasing order of its atomic number. Right? Okay, perfect. So guys, now the question is, what is the SI unit of radioactivity? So this is the next question in which confusion comes. So please remember, Curie is just a traditional unit of radioactivity, it's not the SI unit. So the discoverer, who was he? Henry Becquerel. So the SI unit of radioactivity is Becquerel. What is it? The SI unit of radioactivity is Becquerel. That's BQ. Now talking about Rutherford. So it is another unit of radioactivity. Becquerel. This is the SI unit of radioactivity. And then we have one more unit, that is Roentgen. So these all are the units of radioactivity. But you must remember what is the SI unit of radioactivity, that is Becquerel. It is also denoted by BQ. Fine. Now Manoj, let us say we have a paper. We have this paper. Fine. Now I'll just try to throw a stone over it. It might strike and fall down. But if I'll throw a stone with greater velocity, it will just strike this paper and it will come from backside, right? So here I'm talking about penetrating power. So we were talking about alpha, beta and gamma rays. So yes, we are aware of these are harmful radiations, right? So here, if someone asks you which has the highest penetrating power, so as always remember alpha, then beta and then gamma. So while moving from alpha towards gamma, the penetrating power keeps on increasing. So penetrating power in the increasing order is mentioned here. So just you can see alpha, then beta, and then gamma. So you must remember the sequence order. That's also important. It is from previous year paper only. Okay, that's done. Now guys, uh, one more question was there which I was asking very starting. So what are alpha particles? So alpha rays are actually the helium nucleus. What are they? Helium nucleus. This is the question which is from RRB JEE also, but I'll go in the depth. I'll show some of the reactions as well. Beta rays, what are they? So these are actually electrons. These are electrons. And gamma rays are electromagnetic waves, that is EM waves. So alpha rays are positively charged, beta rays are negatively charged, and gamma rays are neutral. Ionizing power is 100 times greater than the beta rays and 1000 times, 10,000 times greater than the gamma. Beta rays ionizing power is lesser, gamma rays it has very less ionizing power. Penetrating power, gamma ray has the maximum power, then beta followed by alpha. So that's in the decreasing order. Okay, and the speed of gamma rays is similar to the speed of light. Beta ray 9/10 of the speed of light and alpha ray 1/10 of the speed of light. Now, guys, periodic table is it? There's a question, and the question is Pawan is asking: the periodic table, is it mandatory to remember all the elements and their names for the exam? So Pawan, see, I'll tell you the trick in the periodic table. Basically, it would be great if you can remember atomic number till 30. Why I'm saying this? Because in the periodic table, I'll be explaining you the trick. I'll give you some of the tricks how you can learn it up. So if you want, I can give you some of the tricks right now also. So Pawan, please focus on this part. Where is it? Yeah. So guys, let's say I'm aware of periodic table till atomic number 30. So it's like hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, and so on. Now guys, if I know about these tricks, about these blocks, so sir, this is alkali metals, right? Hydrogen is a non-metal. I'll write it for you. Although it's the part of the chemistry is telling you. So it can be linked with some of the tricks like Halina ki rab se faryad, beta mange kanya sundar baap raji. So these were the tricks, but these are tricks are in Hindi medium. So that's why I'm not telling you right now. But yes, you can make your own tricks. So what will happen because of these tricks now, you will be able to remember the whole periodic table. So that's the way. And there are other concepts like if I'll move from left to right, what is going to happen? If I'll move from top to bottom, what is going to happen? I'm talking about the periodic trends. So these things are dependent on this only. So yes, learning up till zinc would be better for examination because others you will be able to link it easily. Is it okay? Yes, in the chemistry part we'll remember that. So coming back with our point, where were we? We have discussed this, right? Yeah. So now guys, let's talk about these rays in detail. Guys, from the periodic table, can you please tell me what is the atomic number of phosphorus? What is the atomic number of phosphorus? See, it will be column wise. Column wise, it would be easy, Apur. So for the phosphorus, the atomic number is 15, right? Hydrogen, helium, lithium, and so on. Thank you, Siddharth. That's 15. Now what happened? So here, beta decay was there. And because of beta decay, there were some changes which were there. So the number which is mentioned below, that's atomic number. This is atomic number. And the number which is mentioned above is mass number. And for phosphorus, the mass number is 32. Okay. So, can you please help me out? Beta ray is what? Is it the helium nucleus or is it the electron? What is beta? That's correct, Siddharth. Guys, please tell me what is beta? Is it the helium nucleus or is it equivalent to electron? What is it? So, say it's equivalent to the electron and it's mentioned here also. Beta ray, electron, right? Okay. Now, we can link it with the basic example. So, what happened? Since it is an electron, so here electron will be emitted. So, -1, 0. I guess this much maths you are aware of. What should I add in 32 if I let 32 with 0, what I'll get? So the answer will be 32 again. But if I add up something with -1, how can I get 15? So sir, when 16 will be added to -1, that is 16 plus of -1 will give you 15. So it will be 16. And the atomic number 16 is for what? Atomic number 16? So atomic number 16 is for sulfur. One second, I'll just show you. See, in the oxygen family, we have sulfur. See, 16, right? So 16 is actually the atomic number of sulfur. So yes, because of beta decay, this phosphorus is converted into sulfur. Understood? So whenever beta decay is there will be no change in the mass number, that is mass number will remain same, but atomic number will be increased by 1. So this will be useful when question will be asked in the examination. So see, in the beta decay of the phosphorus, this phosphorus was converted into the sulfur. Understood? Tell me guys, any questions, any doubts, any queries? That's clear. See, now we are talking about the decay of uranium. From this reaction, tell me, is it the example of beta decay? Very basic question. Is it the example of beta decay? I just want to know the answer in yes or no. So what you will say? Sir, if I talk about the beta decay, we were linking it with the electrons. That is, there would be no change in the mass number, but atomic number will be increased by 1. So it's very obvious, it's not the example of beta decay. No, it's not the example of beta decay. So what is it? Let's try to find it out, right? So guys, we were aware of that if I talk about alpha decay, so these were what? So these alpha is, this was helium nucleus, right? So if alpha decay is there, here what will be the difference? So it's 2He4. So the mass number will be decreased by 4 and the atomic number will be decreased by 2. So this is the example of alpha decay. Okay. So in beta decay, there is no change in the mass number, but atomic number increases by 1. So like this is the case of carbon 14. So here no change in the mass number, but atomic number increased by 1. That is what beta decay is. Okay. What about gamma decay? So neither there will be any change in the mass number nor there would be any change in the atomic number. Here only and only energy level of the nucleus is going to change. So the atomic number and the mass number of the radioactive nucleus are going to remain same. And yes, that's about your gamma decay. So understood? So what's alpha decay, what's beta decay, and what's gamma decay? Guys, are all these three things clear? Tell me. So Pawan Siddharth, if someone will ask you about the question, if there is any equation given, so you can easily understand. Okay, so there's no change in the mass number, no change in the atomic number, gamma decay. So the atomic number is same, but mass number is same, but atomic number is increased by 1, beta decay. So there's a decrement in the mass number by 4 and decrement in the atomic number by 2, alpha decay. That's it. Great, perfect. Okay, so now in the alpha decay, so you'll see that mass number is decreased by 2, atomic number is decreased by 2, right? In the beta decay, mass number is unchanged, but atomic number is increased by 1. In the gamma decay, no change in both the things. In the positron emission, mass number is unchanged, but atomic number decreases by 1. In the electron capture, mass number is unchanged, but atomic number is decreased by 1. That's it. So in our syllabus, only this alpha, beta and gamma would be sufficient, but this is for just extra knowledge. Okay. So this concludes our part, right? So Siddharth, we'll take a random example. So in the beta decay, you can take this example. See, there's an element X. Let's say this is A is representing the mass number and Z is representing the atomic number. So in case of beta decay, what happens? In case of beta decay, since it is electron, right? So it's 0 minus 1. So what is going to happen? The element at Y will be formed. Here there will be no change in the mass number, but the atomic number will be increased by 1, because you are aware of Z plus 1 minus 1 will give you Z only. So that's the point. So here we were talking about sulfur and phosphorus, right? So for the phosphorus, the atomic number was 15, mass number was 32, and since there was beta decay, so what happened? It was electron. So here it was 16, it was 32. So the atomic number of 16, atomic number 16 is of sulfur. That's why phosphorus actually converted into sulfur when we were talking about a beta decay. This is for you, Siddharth. Siddharth Dhawan. This is for you. Okay. Next. Now let's go with the nuclear fission. What is it? So in year 1939, there was a German scientist, Otto Hahn and F. Stresemann, who discovered that when a uranium nucleus is bombarded with a neutron, it breaks into smaller nuclei of comparable mass along with the emission of few neutrons in energy. So the process of breaking off heavier nucleus into smaller nuclei and release with the release of large amount of energy and a few neutrons is called nuclear fission. In short, a larger nucleus, when it splits into the smaller nuclei, during this splitting, energy is also released, and this energy is utilized in nuclear power plants where it is used in the power generation. So this is what nuclear fission is. But if I talk about nuclear fusion, what happens? So the smaller nuclei actually combine together to form a larger nucleus, right? So nuclear fission of the uranium nucleus, it's given here, but in short you must remember this part only. And can you please give me one of the example where this process can be seen? So as already discussed, this process can be seen in the nuclear reactors, but also you must remember about a bomb blast that happened during Second World War in Japan, and the two cities were Hiroshima and Nagasaki. What is that? Atom bomb. So guys, for this process, for the nuclear fission process, we need some fissionable material. So what are they? So these materials are the radioactive elements which undergo fission in a sustained manner when it absorbs the neutron. So here we can also say that these are fissile materials. Example can be uranium-235 or plutonium. Now, why only 235? Why not 238? Because 235 is fissile material. It's not 238. So see, all the isotopes of uranium do not undergo nuclear fission when they absorb neutron. Like natural uranium consists of 99.28% of uranium-238 and 0.72% is having uranium-235. So do you know what is it? See, uranium-238 and uranium-235. I'll write the atomic numbers for you. So that is 92. Now tell me one thing. 1 second. Yeah. So guys, tell me one thing. What is the atomic number in both the cases? The atomic number in both the cases is 92, which means, see, atomic number is always equal to the number of protons, which means the number of protons in both the cases is also 92, right? So there's a term which is known as isotope. Isotope. Do you know what is it? The word iso actually means same. What does it mean? Iso term means same, but what? So this, what is it? P can be linked with the protons. If two elements have similar number of protons but different mass number, they are considered to be isotopes. So here, these are actually the isotopes of uranium. Understood? So out of these, uranium-238 does not undergo fission, but uranium-235 undergoes fission. That's why uranium-235 is a fissionable material and 238 is not. So there are some radioactive materials or elements which can be converted into fissionable material. They are known as fertile materials. So I guess this part is clear now. Understood? So plutonium 239 or uranium 235, these were fissionable materials. That's the point. You are saying there's a difference in the, so same atomic number but different mass number. That's correct. True. So guys, we were talking about atom bomb. You need not go with the structure. No one is going to ask about the working. But you must remember one thing. Who discovered it? So I gave you the idea. I gave you the trick. How to remember this? So guys, whenever this atom bomb will blast, many people will die, right? And in Hindi, for the death we use a term that is mar. So during a bomb blast, sir, people will die the high amount, right? So it's many people will die in the high amount, not only in the closed area but also in the open area. So Oppenheimer was the one who discovered this atom bomb. Fine. So the two bombs which were dropped in 1945 at Hiroshima and Nagasaki during World War II, what were they? So you must remember these names. First bomb was Fat Man, and the another bomb was Little Boy. So Fat Man and Little Boy were the two bombs that were dropped on Hiroshima and Nagasaki. Right? So that's correct. Perfect. Proceeding further. So as we have discussed about the fission, what was it? Sir, a larger nucleus was splitting into two different parts, right? This was what? This was fission. But in the fusion, just opposite happens. What happens in the fusion? The smaller nuclei actually combines to form a larger heavy nucleus. So energy can be produced when heavier nucleus splits up into two smaller nuclei. Similarly, energy can also be produced when two lighter nuclei combine to form the heavier nucleus, and this is what fusion is. Now, for this nuclear fusion, can you please tell me where it is used? So guys, this process takes place in hydrogen bomb. Where? In hydrogen bomb. Not only hydrogen bomb, so it is also the reason for our survival. That means I'm talking about what? Who will tell me? Why I'm saying that nuclear fusion is actually responsible for the human survival. What's the reason? Exactly my point. So, Apur, you are correct. I'm talking about sun. So not only hydrogen bomb, but also this process is taking place at sun, because of which the energy is released, and yes, that energy is sent to earth, and because of that energy only photosynthesis is taking place, because of which plants are able to make the food, and because of that food only we are able to survive, right? So they are continuously, this conversion is taking place. That's correct. Okay, so nuclear fusion, hydrogen bomb and sun, nuclear fission, nuclear power plants and atom bomb. So nuclear fusion is clear now. So what's the difference between two? Let's understand. So this is for the nuclear fission and this is for the nuclear fusion. So what is the difference between two? In the fusion, so it's the combination of two lighter nuclei to form a heavier nucleus. In the fission, the process of breaking up of the heavy nucleus into smaller nuclei. Nuclear fission, so it can be performed at the room temperature, but for the fusion, very high temperature and pressure is needed, like that of sun. Alpha, beta, gamma radiations are emitted in nuclear fission. In fusion, alpha rays, positrons and neutrinos are emitted. Fission. So fission leads to the emission of gamma radiation. This triggers the mutation in the human gene and causes the genetic transform diseases. Fusion, only light and heat energy is emitted. Okay. So now it's clear what was fusion and what is fission, right? So yeah. So now talking about this radioactivity, guys, where this radioactivity is used. So here we have already taken the example of uranium 235 in the nuclear power plants. But if I talk about some of the radioisotopes, Here also we can talk about the use of the radioactivity. So the first part is with agriculture. Then I'll tell you about the medicines as well. So the radioisotope of phosphorus, where is it used? So it is used in increasing the productivity of the crops. So that's about agriculture. But guys, have you heard the term? I guess Siddharth, you were there in and Apur, you were also there in the bio classes. There's an issue that is known as goiter. Remember? What is it? So goiter was the issue in which this neck portion actually feels like that swelling is there. So it's because of what? So whenever there would be the deficiency of the iodine in our body, these glands actually start swelling, right? This is because of iodine deficiency. So in order to treat this goiter, we need to use iodine only, but iodine's isotope. Which isotope? So that is iodine 131. So we have different isotopes for the medicine purpose. So we can talk about the diagnosis or the therapy part. So isotopes are used as a tracers to diagnose the nature of circulatory disorders of the blood, defects of the bone metabolism, to locate the tumors. So here we'll start with the radioactive sodium first. Radioactive sodium is used for the effective functioning of the heart. Radioiodine, that is iodine 131, is used for the curing of the goiter. Radioiron, that is iron 59, is used for the diagnosing of anemia and for the treatment of the same. One more thing, which Siddharth you were saying, we were talking about uh, what one thing, what was it? Carbon dating, yeah. So Siddharth, let's say there's a stone which is found and someone is asking that this is how many years old. So what you'll do? You'll go with carbon dating there, right? So here in the archaeological research, carbon dating plays a very crucial role in determining the ages of those old paintings, earth, fossils. So it is radiocarbon dating basically, right? So yes, one of the devices also there, that is dosimeter. So dosimeter is the device that is used to detect the levels of exposure to an ionizing radiation. So here, since we are talking about the radiation, so we need to discuss about the nuclear power plants too. So we'll be starting with the nuclear power plants now. So what are nuclear reactors? So there are different types of nuclear reactors. It may be the breeder reactor, it may be the fast breeder reactor, pressurized water reactor, pressurized heavy water reactor, boiling water reactor, water cooled reactor. So all these reactors are of different types, and according to the need, it's built in the different parts of the world. Now, so for the functioning of this, one second, it's not about archaeological research. This is about nuclear reactors. So the essential components of the nuclear reactors are fuel, moderator, control rod, coolant, and the protection valve. So guys, for the proper functioning, we need a fuel. For example, if I need to ride a motorbike, I'll need petrol. In the similar manner, if I want to run this nuclear reactor for the power generation, I need a fuel. So what is it? So fuel is basically the fissile material which is used, and the commonly used fuel material is uranium. Can you please tell me which isotope? So that is uranium 235, right? Okay. Next, so Apurv, it goes in a manner. So you might have heard about the life lifetime, and you might have solved the numericals regarding same, right? So yes, it continues to proceed, and it goes for the lifetime, and it goes till the time that particular element is surviving. That's it. So it was half lifetime. We used to denote it by T half, right? I'm talking about that. Okay, so coming back to our topic. So what was it? Yeah, fuel. So in order to run the motorbike, in order to run the train, so we need some fuel, right? So petrol, diesel, they all are used as fuel. So similarly in the nuclear power plants, we need something for the fuel, and these are fissile materials where uranium is the perfect example, and the isotope of that particular uranium is uranium 235. Okay, now guys, when this energy or power generation is there, so during this energy production, there is huge amount of energy basically, right? So there's the bombardment of the neutrons. So in order to control that bombarding of the neutrons, what we use? So in order to control that bombarding of the neutrons, we need to use moderator. What we need to use? We need to use moderator, and here the best moderator will be the graphite and the heavy water. Guys, I'll take the next page and ask, can you please tell me the formula for the hard water? Anyone? What is the formula of the hard water? And I want the answer from each and every candidate basically. Why? Because this is the question which will lead to negative marking. Siddharth, Apurv, please open your ears and close one of them, because the thing that I'm going to tell you is very important. What is it? Hard water is just a water that was H2O. The only point is here dissolved salts of calcium and magnesium are there, or we can say calcium and magnesium ions are there, right? Hard water is same. But if I talk about heavy water, that's correct, Siddharth. Heavy water consists of deuterium. So here it is just H2O in which dissolved salts of calcium and magnesium are there. But since we are talking about heavy water, you are absolutely right, that is D2O, where D is deuterium, that is the isotope of hydrogen. Okay, so graphite and heavy water are the isotopes, graphite and the heavy water are the moderators. Then talking about the protection wall. So a thick concrete lead wall is built around the nuclear reactor in order to prevent the harmful radiations from escaping into the environment. Talking about the coolant, so that is used to remove the heat produced in the reactor core to produce the steam. Okay, so electricity, water, air, helium, they are some of the coolants which are used. Fine. Yeah, hard water is related to the saponification. I'll give you the best perfect example. So what happens? That's the part of chemistry basically, but since you are asking, I'm telling you. So if you are going with the hard water, and if you wanna clean your clothes, soap will not work there. Why? Because that soap will not generate foam. Right? So yes, that is again used for in the moderator part only. So Siddharth, what I was talking about? I was talking about something, right? 1 minute. Extremely sorry. Uh, yeah, I was talking about hard water. So guys, if soap is not working in that harsh conditions, that is in the hard water, what we can use? So for that we will go for uh, detergent, and that's why we say that detergent are superior to the soaps, as these detergents are able to work in the hard water as well. Okay, so this coolant is done, protection wall is also done. Okay, and yeah, protection wall, why it is so? Because these are harmful radiations and they might escape the environment, it might create issue for us. So that's why these are very thick walls which are created in order to prevent us or the all the plants and animals from these harmful radiations. Okay, next. So let's talk about the nuclear reactors in India. So as of now, we know that that is Bhabha Atomic Research Center, that is BARC, and that's in different cities of India, which includes Vadodara as well. Obviously, it's there in Mumbai. So nuclear power plant is the nuclear power is the fifth largest source of power in India. But you need to remember two names. Tarapur Atomic Power Station is India's first nuclear power station. So we have other power stations in Maharashtra, Rajasthan, Gujarat, Uttar Pradesh, Tamil Nadu. Tamil Nadu is in Kalpakkam and Kundalkulam. And second name is Apsara. This is the first nuclear reactor built in India and Asia. So there are 22 reactors basically, and some operating reactors name is Cyrus, Dhruv, and Purnima. Right? So yep, that's Trombay exactly. So guys, these were the nuclear reactors which are present in India. And from the physics part, that's all from my end. Guys, we have discussed this invention discoveries in the previous class, but I have still kept this PDF. Please revise these names of the inventors and the discoverers, as these questions are asked every time. So directly, indirectly, it may be asked in the examination. So there were some questions like who discovered X-ray. So these type of questions are asked in the examination. And one more question from the previous part of your CGL is that who discovered the dynamite. So dynamite was discovered by Alfred Nobel, right? So yes, these invention discoveries are important for examination. You must revise it from here. So I'm just sharing this PDF, and in the next class we'll be starting with the chemistry. So I'll request you all to join sharp at 1 p.m. in the next class, and the topic will be atomic structure. And for understanding that atomic structure, I have some animations as well. In the chemistry, I'll be using some animations. But yep, if you have any doubts or queries, you can just let me know. Yeah. So yep, Alfred Nobel was the one who discovered this dynamite. True. So thank you, Siddharth. Thank you, Pawan, and all the other candidates who joined live. So thank you for being such a wonderful audience. We'll meet sharp at 1 in the next class, and we'll start with the chemistry. So I'll request you all to bring your pen and pencil also, as I'm going to teach you the atomic structure. So in the first class itself, I'll be telling you how that formula 2n square works. So that's important. Okay, Manoj, Pawan, Apurv, Siddharth. Bye bye guys. Take care. Jai Hind. Love you all.